Good morning to all my dear students. Welcome to the another lecture in the Unit 1 Chemistry of the Hydrocarbons in the Petroleum. It is the lecture number 3. As we have read about the various types of the hydrocarbons in the crude oil, which is the fundamental requirement to understand for the crude oil refining process. How much percentage of the hydrocarbons and which kind of the hydrocarbons are present in the crude oil determine the quality of the crude oil. Now we should understand the various hydrocarbon chemistry in this lecture. The outline of the presentation is the review of the previous lecture, the objective or the learning outcome of this lecture, the introduction, chemistry of the paraffins in the petroleum or the crude oil, the cycloparaffins, the properties of the paraffins, the olefins, the naturally occurring olefins, the properties of the olefins. Then we have a small exercise and references with SELO. The objective or the learning outcome of this lecture, as the petroleum products are those materials derived from the crude oil and it is processed in the oil refineries. So the refining process, we should know the fundamentals of the crude oil hydrocarbons and the chemistry of the hydrocarbons to understand its treatment and the removal purpose in the refining. We have discussed all the following points in the previous lectures: the origin of the crude oil, the composition, the classification of the crude oils, and the hydrocarbons in the petroleum. The paraffins word given for the saturated hydrocarbon derived from the Latin word which is having the little affinity, or we can say not much affinity, a reference to its chemical unreactivity. So the word is given to the saturated hydrocarbons, the paraffins, which is having the little affinity, which is going to reflect its chemical unreactivity. The paraffins, which are also called alkanes, having the general formula CnH2n plus 2, where N is the number of carbon atoms. And we can have two types of the paraffins. We have normal and isoparaffins, depending on its structure, the straight chain and the branch chain. The normal paraffins are simply written as N-paraffins, or we can say N-alkanes. They are the open and the straight chain saturated hydrocarbons. The isoparaffins, which are branch chain hydrocarbons, and it begins with the number 4 carbon atom, that is isobutane, which is also known as methyl propane. The structural formula is different, but its molecular formula is same. So they are both the structural isomers. The hydrocarbons can also exist in the form of ring or the cycle, that is cyclic paraffins or the cyclic saturated hydrocarbons by adding the prefix cyclo to the name of the alkane. It is also based on the number of the carbon atoms. The condensed structure representation without the carbon or the hydrogen is convenient to write up the cyclic alkanes. Here you can see this is the cyclic paraffin, which is having 3 number of the carbon atoms, which is having the cyclopropane. Either we write cyclopropane like this, or either we have this representation. This representation is also giving us the cyclic propane structure. Similarly, you are able to see here the 4 carbon atoms, which is having the closed structure, cyclobutane, cyclopentane, cyclohexane. So it is having the, according to the number of the carbon atom, it is having the homologous series. Now let's discuss the physical properties of the paraffins. The melting point and the boiling point of the paraffins increases with the increased molecular weight. Here we can see one example, that is of the 1 carbon atom, methane, whose boiling point is 164 degrees centigrade. And another example, that is decane, that is the number of the carbon atom in decane is 10. Its boiling point is 174 degrees centigrade. So why the melting point and the boiling point increases with the increased molecular weight in the straight chain hydrocarbons, that is paraffins? The reason is the increase in the surface area. Surface area is increasing or not? Yes, it is increasing. So as the surface area increases, what happens? It increases the van der Waals force of the attraction between the molecules. Intermolecular attraction increases. That's why the melting and the boiling point increases. And if we talk about the branch chain paraffins, what happens? One example we take of the methane, another example we take the isobutane, that is the branching, that is the branch chain paraffins. The boiling point decreases in that because in the branching the decrease in the surface area causes. So if we have the long chain normal carbon atoms, like we have the branching starts from the 4 number of the carbon atoms, that is the butane. This is butane. And if we talk about the isobutane, that is, this is the chain, branch chain. We have the 3 in this and 1 it goes on branch. So this is to be the structure. So have you seen it causes the decrease in the surface area? Yes. In the branching, the surface area is decreases. And in the straight chain, we go for a long chain, straight, that increase the surface area. So now you better understand this branching, which is causing the decrease in the surface area. That's why the boiling point, decrease in the surface area, decreases the van der Waals intermolecular force or attraction, which causes the decrease in the boiling point. Understood? So the boiling point of the isobutane is lesser than the normal butane. But the melting point is increases in the branching. Why? Because the melting point depends on how easily the molecules are closer one another and how they are easily stacked out. So in which you can say the more easily arrangement of the atoms are there, more closer, more easily stacked. So that is the more easily stacking possible in the straight chain hydrocarbons. So that's why the melting point increases. Clear what is the reason? So the paraffins melting point and boiling point. Melting point depends on the, if we are talking about the straight chain hydrocarbons, so they go with the molecular weight having the large surface area, so both goes on increasing depending on the intermolecular attraction. But in branching, the melting point depends on the how easily the stacking is possible and the surface area for the boiling point. Non-polar substances are not water soluble. Alkanes are less dense than the water and swim on the top of the water. So they are less dense and they float on the water, can easily seen because their density is lesser than the water. Now we see the chemical properties of the paraffins. As we know, the paraffins is having the little affinity towards the reagents, so they are relatively inert chemically. Most of the reactions require the specialized catalyst for breaking down the carbon-carbon single bond. So they are very strong bond saturated hydrocarbons, but if we see their reactions, the most important burning or the combustion reaction and the oxidation, so both these reactions are very important reaction using the alkane as a fuel. So that's why they are used as a fuel, and they go for burning or the combustion reaction, which is highly exothermic, and these fuels which is used in the engines require the additives to improve the combustibility for the smooth and efficient burning. So in these hydrocarbons, the proper additives are mixed up for enhance and smooth and efficient burning of the combustion reactions. So here you can see their most common reactions of methane. It goes on burning and produce the enough amount of the energy. Similarly, the butane. So all the alkanes, these burning and the oxidation are the two important things to be used as a fuel in the engines. So now let's talk about the second important hydrocarbon, that is olefins. That is the unsaturated hydrocarbons, and the hydrocarbons which is having the double bond between the two carbon atoms, that is termed as the alkenes and the olefins. Why the alkenes are called olefins? Because they form oil-like products, oil-like liquids on the reaction. For example, on the reaction with the chlorine gas, it forms the liquid oil-like product. So that's why these are termed as the olefins. And it is having one sigma and one pi bond, and it is quite reactive than the paraffins because of that. The general formula we all know about the olefins, that is CnH2n, 2 hydrogen less than the alkane. It is having how many hydrogens are there in the alkenes? The hydrogens are 4. Understood? And lesser than the alkane if we talk about methane. Ethane also C2H6. Now the carbon atom is in sp2 hybridized and all the single bonds are sp2 orbitals overlap with the orbitals from the hydrogen or the carbon. Understood? So with undergo the sp2 hybridization, we have the overlapping and the unused p orbitals join side to side overlap to form the pi bond. So pi bond is formed by the sidewise overlapping of the p orbitals. The p bond prevent the rotation in the system, and it also responsible for the geometrical cis and trans isomers. In the stereochemistry, if we talk about the geometrical isomers, they possesses the cis and trans isomers. So let's have the structure along. We are talking about the sp2 hybrid orbitals. So due to the sidewise overlapping, this is formation of the pi bond, and this is sp2 hybridized orbital with a hydrogen to the carbon with the angle 120 degree it is. So this is the sp2 hybridization found in the olefins and having the planar structure. Understood? Of this we are talking about the ethylene. So this is the arrangement and how the bonding is taking place with the hybridization. Do you heard about naturally occurring olefins? What is that? Means the alkene structures are also found in some interesting natural sources. Limonene is a natural substance found in the lemon oil. Turpentine, it's a paint thinner found in the pine trees. Here you can see the structure of both. The limonene is having the alkene structure, the carbon double bond. You are able to see here and here. And the turpentine. Hey, this is the structure and you have these alkene carbon double bond. So that is a paint thinner found in the pine trees. Yeah, we have heard how the ethylene and olefins are prepared synthetically, but the alkene structures in natural resources are also there. Another example of the olefin is a very important and famous example you all know. The compound shaped like a saucer ball and having the football-like structure, it is named after Buckminster Fuller, who proposed such structures called fullerene. It's a buckyball having the carbon 60. This is all having this alkene structures. Now let's talk about the property of the alkenes. The alkenes, like the alkanes or the paraffins, are the non-polar materials having the lower boiling point as compared to corresponding alkanes. Why the alkene is having the lower boiling point? Because alkene is having the pi bond. Yes. And paraffins or the alkane is having the sigma bond. Okay. All bonds in the paraffins are the sigma bonds, but in alkenes it is the pi bond is having, which is weaker than the sigma bond. It can easily break out the pi bond. That's why it is having the lower boiling points. Understood? So presence of the pi bond require less energy to break and it is weaker. That's why the alkenes is having the lower boiling point, and the alkanes are stronger, having the high boiling point. Alkene also have the strong odors, sometimes the pleasant and sometimes not. Here we can compare the alkanes to the alkenes boiling point. We have the pentane boiling point. Pentane is the paraffin. It is having the boiling point 36 degrees centigrade, while if we talk about to the pentene, same number of carbon atoms. Okay, in pentane the number of carbon atom is 5. In pentene also the number of carbon atom is 5. But there is the double bond. So the boiling point decreases. That is 30 degrees centigrade. Understood? So, and here we can have two type of the pentene. Then we have the one pentene and two pentene. But their both boiling points are lesser than the pentane. Understood? The next one is the chemical properties of the alkene. If we see, the alkenes are quite reactive than the alkanes. A very common and important reaction of the alkene is hydrogenation reaction. What is hydrogenation? The addition of the hydrogenation to the double bond in the presence of the catalyst. That is also called the catalytic hydrogenation. And this is very important reaction of the olefins and the alkenes. It goes on the addition of the hydrogenation. It is generally done for the oils to convert into the fat, because oils are the unsaturated hydrocarbons which generally converts in the saturated hydrocarbons. So conversion from unsaturated hydrocarbons to the saturated hydrocarbon, and this most important reaction is called hydrogenation. So here you can see the various alkene hydrogenation and heat of the hydrogenation. When the hydrogenation reaction takes place, it is highly exothermic, and we can have the various heat of the hydrogenation of various olefins, the straight chain as well as the branch chain, and you can able to see the hydrogenation heat that goes on decreasing as the number of the carbon atoms goes on increasing. Another important class of the reaction or the property shown by the alkene is the addition reaction, addition of an electrophile to the double bond, which is called electrophilic addition, which is very important. Electrophile is the electron deficient species generally attacked to the site where the electron rich species is there. So it produces a positively charged carbocation, and a nucleophile reacts with the carbocation to complete this two-step reaction. Here you can see the first step reaction. In the presence of the electrophile, we have here this pi bond delocalized, and here we have the positive site and the negative site appear due to the delocalization, and the electrophile attack towards the electron rich species, because electrophile is deficient and it attacked to the electron rich species. So here it comes an intermediate. So this is the intermediate, and the positive charge occurs on the carbon, another carbon atom which is having this intermediate called carbocation. So when this intermediate form, the nucleophile, which is the electron rich species, it goes with the this positive charge carbocation and the product is formed like this. We have the nucleophile attached to this position. So this how it's a two-step process forming an intermediate. Okay. The first step is attacking of the electrophile, and then the intermediate carbocation is forming, and then the nucleophile is attaching to that carbocation to lead to the final product. So in case of the symmetrical alkenes, the electrophilic addition takes place in a two-step process forming an intermediate. But in asymmetrical alkenes, the electrophilic addition having the different products depending on the rule that is called Markovnikov rule. So we have the symmetrical and asymmetrical example here. You can see here the symmetrical alkenes are those alkenes in which near to the double bond the number of the carbon atom is same. And asymmetrical, near to the double bond we have the different number of the carbon atom. Understood? So in asymmetrical alkene, how the electrophilic addition occurs? It occurs due to the following the rule, that is Markovnikov rule. What is this rule? This rule say that the electron deficient species will attach to that carbon having the more number of hydrogen atoms. So here you go for having the hydrogen, number of the hydrogen atom you have to see. So here the 3 hydrogen atom is there, here it is 1 hydrogen is there, okay. And here how many? 2, okay. This is, so if we talk about the reaction with the water, okay, this asymmetrical alkene causing the reaction with the water, we have H plus and OH negative. Okay, so that is the electron deficient H plus and OH is the nucleophile. So where the addition of the H plus hydrogen ion is there, where the addition takes place of the OH ion. So according to the Markovnikov rule, the hydrogen that is electron deficient attached to that number of the carbon atom which is having more number of hydrogen. So you have to see the number of hydrogen atom. The number of the hydrogen atom is higher at this carbon. So hydrogen will add to this carbon having the major product. And the OH ion will go for adding towards the lesser number of hydrogen, that is this side. So this is called the Markovnikov rule, where certain additions that do not occur by this electrophilic mechanism, it undergo the anti-Markovnikov additions also. The orientation of the substituents in the product is a result of the reaction mechanism in the crude oil. Typical examples we can say the acetic acid, benzoic acid. So generally they go with the addition reaction and undergo oxidation, which is responsible for causing the corrosion. And therefore it is very much effectively handled. These olefins and alkenes are to be strictly handled in the crude oil because they are responsible for undergoing the corrosion because they are quite reactive. Understood? So here the bromination, the symmetrical alkenes, you can say the bromination is there. The unsymmetrical alkenes according to the Markovnikov rule, it takes place hydrogen bromide, and there are some non-electrophilic addition reactions also which is the opposite to the Markovnikov, that is anti-Markovnikov additions, non-electrophilic addition reactions shown by the alkenes. So in symmetrical and asymmetrical addition, it is according to the Markovnikov rule. There we have seen, there is the examples of the aromatic alkenes here and the non-electrophilic additions. Now, there are the questions on the basis of the chemistry and the properties. We have read about the paraffins, olefins, and the electrophilic additions. So go through it. These are the references which we have followed for this topic. So these are the two important SELO for this lecture that should be fulfilled: the application concept of the topic and the adaptive thinking skills. Thank you and take care.